Bismillahirrahmanirrahim. My dear student, I am Dr. Muhammad Yaseen. Today we are going to discuss a very important topic of chemistry, that is the pericyclic reaction. Always remember that the pericyclic reactions are very important, not only from the examination point of view but as well as from the synthetic point of view. I have not seen any of the chemistry examination in which people have not asked about the pericyclic reactions. So what are the pericyclic reactions? It is a fundamental lecture about the pericyclic reactions. In the coming lectures I will teach you what are the types of the pericyclic reactions and how they differ from each other. So let's move towards our topic of pericyclic reaction. Student, I am Dr. Muhammad Yaseen. This is our second lecture on Introduction to Pericyclic Reaction. In the first lecture, we have studied what are pericyclic reactions and what are the characteristics of pericyclic reactions. Additionally, we have learned that how one can assign the symmetry to the p orbitals. In the previous lecture, we have studied that the p orbitals have two types of symmetry: mirror plane symmetry and the C2 symmetry, or the center of the symmetry. And we have additionally also studied how these p orbitals overlap with one another with reference to molecular orbital theory. This is our second lecture on Introduction to Pericyclic Reaction. So if you have not yet studied the part 1 of this lecture, so I recommend you first to go through that lecture and then proceed to the part 2 of this lecture. So let's move to our main topic today. Today we will learn the symmetry of p orbitals in 1,3-butadiene. I have selected the 1,3-butadiene as a system that is having multiple number of p orbitals. We will study the symmetry of p orbitals in simple 1,3-butadiene system. We will study the symmetry of p orbitals in the 1,3-butadiene in the cation form. We will also study the symmetry of p orbitals in the anion form of 1,3-butadiene. We will also study the symmetry of p orbitals in 1,3-butadiene, that is in allyl in the free radical form. So there are three forms of the 1,3-butadiene. One is the neutral, the other is cationic form, the third is the anionic form, and the fourth is the free radical form. So we will study these four forms of the symmetry of p orbitals in the 1,3-butadiene. Similarly, we will also study the symmetry of p orbitals in the allylic system. Similar to the 1,3-butadiene, we will also study the fourth form of the allylic system, the neutral allylic system, cationic, anionic, and free radical allylic system. We will also study the symmetry of p orbitals in 1,3-pentadienyl system, and at the last we will study the electron filling concept in conjugated systems that will integrate the homo-LOMO concept. What is homo? Homo means highest occupied molecular orbital, and LOMO stands for lowest unoccupied molecular orbital. So from the electron filling concept we will derive the concept of homo-LOMO. So this is the summary of the these are the key concepts of the today's lecture that we are going to discuss. So move to our lecture. Symmetry in 1,3-butadiene. First of all, we are going to discuss the symmetry of p orbitals in neutral 1,3-butadiene. 1,3-butadiene, in 1,3-butadiene, each carbon atom is sp2 hybridized and have one unhybridized p orbital present on each carbon atom. So there are 4 p orbitals present on the 4 carbons of 1,3-butadiene, and these 4 p orbitals can overlap with each other in multiple forms. On the bottom of this slide I have shown the 2 resonating structures of the 1,3-butadiene. In the first resonating structure I have shown a double bond between carbon number 1 and carbon number 2, and another double bond between carbon number 3 and 4. Whereas in the second resonating form I have shown a double bond between the carbon number 3 and 4, and positive and negative charge are shown on the terminal carbon atom. On the top of these 2 resonating structures I have shown a dotted resonating structure of the 1,3-butadiene, showing that the double bond is present between all the 4 carbon atoms. Since each carbon is having 1 p orbital that can overlap with the other p orbital, so according to the molecular orbital theory, when 4 atomic orbitals are overlapping, 4 molecular orbitals will be formed. Out of these 4 molecular orbitals, 2 will be bonding molecular orbitals and the 2 will be the anti-bonding molecular orbitals. The first molecular orbital, that is the bonding molecular orbital, I have assigned it a wave function psi1. To the second bonding molecular orbital, I have assigned the wave function value psi2, and to the third anti-bonding molecular orbital, I have assigned the value of psi3 star, whereas to the fourth anti-bonding molecular orbital, I have assigned the value of psi4 star. Now, in the first bonding molecular orbitals, I have arranged the p orbitals in such a manner that all the 4 p orbitals having the positively assigned lobes on the upper side and the negatively assigned lobes on the lower side. So the p orbitals are overlapping effectively, all the 4 p orbitals are overlapping effectively, and there is no node present between any of these 4 p orbitals. What is node? Node is a value of the psi function equal to 0. The place where the value of the wave function becomes 0 is called node. In the p orbital, where is the node? Node is the region of interconnecting the 2 lobes, that is positively assigned lobe and the negatively assigned lobe. So in that region, in the p orbital, you may see that there is no value of the, there is a 0 value of the psi function, so there is a node present in a p orbital. Each p orbital is having one node. So in the psi1 or the bonding molecular orbital, when the 4 p orbitals are arranging them in such a way that their same sign lobes are present on the same side, either negatively charged or negatively assigned lobes are present on the upper side or on the lower side, it doesn't matter. So all the 4 p orbitals are overlapping and there is no node. All the positively assigned lobes overlap with each other and negatively assigned lobes overlap each other, and hence there is a no node present in this psi1 bonding molecular orbital. So what is the symmetry of the p orbitals in psi1 or bonding molecular orbital? For the sake of simplicity, I am discussing only the symmetry of the middle 2 atomic orbitals. So in the case of psi1, you have to number the p orbitals from the left to right. So the first one is the from the left side is the first p orbital, the second is the then comes the second p orbital, then comes the third, and last is the fourth orbital. So whenever I am talking about the number of p orbitals, you have to count the p orbitals from the left towards the right. So I am talking, for the sake of simplicity, the symmetry of only the second and the third atomic orbitals. So in the psi1, if we talk about the symmetry of the second and the third p orbitals, what is symmetry, what kind of symmetry is present between the second and the third atomic orbitals? Definitely they are the mirror image of each other, and hence they have mirror plane symmetry. Since they are the mirror image of each other, since the positive lobe of the second and the third p orbitals are present on the upper side and the negatively assigned lobes are present on the lower side, and hence they have the mirror plane symmetry. In the table, I have shown the 4 columns. The first column on the left side is that of representing the node, and the second is representing the orbitals, and the third is representing the molecular mirror plane symmetry, and the fourth is representing the center of symmetry. So in the case of molecular orbital that to which I have assigned the wave function value psi1, what kind of symmetry is present in it? It has a mirror plane symmetry. So in the mirror plane symmetry, I have written the word S. S denotes that the symmetry is present. Do it have the C2 symmetry or center of symmetry? No, it does not have C2 symmetry. So in the C2 column for the psi1, I have written the value A. A denotes that the C2 symmetry is absent. In the case of second bonding molecular orbital to which I have assigned the psi2 value, one node is present. One node is present. This node is present, as I have already informed you that for the sake of simplicity, I am talking or discussing the symmetry of only the middle two atomic orbitals. So you may see that between the atomic orbital or the p orbital number 2 and the p orbital number 3, one node is present. The positive assigned lobe of the second p orbital is on the upper side, whereas the positively assigned lobe of the third p orbital is present on the lower side. So the atomic orbitals can only overlap if they have the same sign of the lobes in front of each other. And here in this case, the positively assigned lobe of the second p orbital is fronting the negatively assigned lobe of third p orbital. So the overlapping of the second and the third p orbital is not possible, and hence one node is present between the second and the third p orbitals. So, however, the first and the second p orbitals can overlap with each other. Similarly, the third and the fourth p orbitals can overlap with each other. So, one node is present between the third and the fourth p orbitals. In the case of the, if we talk about the symmetry of the p orbitals, so we are discussing only the symmetry of the middle two. So we will discuss the symmetry of the second and the third p orbitals in the case of Psi2. Since these are the two second and the third p orbitals are not the mirror image of each other. So the mirror plane symmetry for the case of Psi2 is absent. So that is why in front of the Psi2 I have written the word AA, mean that M1 symmetry is absent. And whereas these two p orbitals, that is the p orbital number 2 and the third, have the C2 symmetry. So that is why in the case of C2 I have written the S. It means that the symmetry is present. How many nodes it has? It has the one node. Number of nodes can be defined by a general formula n minus 1, where n stands for what? This is the question that is I am leaving for you. I am frequently discussing this formula, and hopefully you will understand what is the meaning of n. You have to comment in the comment section of this lecture what is the meaning of n. So this is your quiz. So in the case of the two bonding molecular orbital, in the case of the first bonding molecular orbital to which I have assigned the wave function psi1, it does not have any kind of the node. So it has the lowest energy. As the number of the nodes increases, the energy of the orbital increases. So the psi1 is having 0 node, has the lowest energy, and have the M1 symmetry, and the C2 symmetry is absent in the psi1. Whereas in the case of the Psi2, it is having the one node, and it has M2 symmetry, and it has the C2 symmetry, and the M1 symmetry is absent in the case of Psi2, and it has the higher energy than the Psi1. If we talk about the anti-bonding molecular orbital, the Psi3 star, in the case of the Psi3 star, the p orbital number 2 and 3, the negatively assigned lobes are in front of each other, and the positively assigned lobes are in front of each other, and hence they have mirror plane symmetry, and the C2 symmetry is absent, and the same is written in the table for the Psi3 star. In the M1 I have written the word S. S stands for that the symmetry is present, and in the C2 column in front of the Psi3 star I have written the word A. A means that the symmetry is C2 symmetry is absent. How many nodes it has? According to the general formula, here the n is the 3. So 3 minus 1 is equal to 2. So it has 2 nodes. The Psi3 star or the antibonding molecular orbital Psi3 star has 2 nodes. Where are these nodes located? The first node is located between the p orbital number 1 and the p orbital number 2 if we count the numbering from the left towards the right. So the first lobe is present between the atomic orbital number 1 and 2. You may see that the positively assigned lobe of the atomic orbital number 1 is in front of the negatively assigned lobe of the second orbital. Where is the second node in the psi 3 star, this second node is present between the atomic orbital number 1 and atomic orbital number 4. You may see that if you ignore the atomic orbital number 2 and 3 in psi 3 star, that is the middle two atomic orbitals, if you ignore, then you may see that the positively assigned lobe of the first orbital is in front of the negatively assigned lobes of the atomic orbital number 4. So it has two lobes. If we talk about the psi 4 star, or the fourth antibonding or the fourth molecular orbital, that is the antibonding molecular orbital, in the case of the psi 4 star, n minus 1 is equal to 3. Here n is equal to 4. So it has the 3 nodes. And if we talk about the symmetry of the p orbitals, the middle two are having the C2 symmetry. So in the case of in the table, you may see that this for psi 4 star, in the C2 column I have written S. S means that the symmetry is present. And for M1, they are not the mirror image of each other. So the M1 symmetry is absent. How many nodes are present? According to the formula n minus 1, here n is equal to 4. 4 minus 1 is equal to 3. So 3 nodes. Now we have to locate where are these nodes. The first node is present between the atomic orbital number 1 and 2. The second node is present between the atomic orbital 2 and 3. And the third node is present between the atomic orbital number 3 and 4. Since the highest number of nodes are present in psi 4 star, so it is antibonding molecular orbital having the highest energy, whereas in the case of psi 1 there is no node or zero node present in its molecular orbital, so it is having the lowest energy. So this was the symmetry in the case of neutral 1,3 butadiene. From this concept, we may derive another very important concept, that is the homo-LOMO concept. First of all, let me know which of these molecular orbital is having the lowest energy. Obviously, the one which is not having any kind of node. And here in this example is that of psi 1. Psi 1 is not having any kind of node. So this molecular orbital is having the lowest energy. Now, my second question is, which molecular orbital is having the highest energy? You will say that psi 4 star, because it has the 3 nodes. So if we compare the 0, 1, 2 and 3 nodes, the molecular orbital that is having 3 nodes have the highest energy. HOMO, highest occupied molecular orbital, and LOMO, lowest unoccupied molecular orbital. In the case of 1,3 butadiene, how many electrons do you have? 5 electrons do you have? 4. So according to the electron filling model, first 2 electrons will occupy the psi 1. The second 2 will go into the psi 2. So which one is the highest occupied molecular orbital? In the case of 1,3 butadiene, it is psi 2, because in the psi 2, 2 electrons are present. So highest occupied orbital is psi 2 in the case of neutral 1,3 butadiene. So this is the HOMO of the 1,3 butadiene. Psi 2 is the HOMO of 1,3 butadiene. Which is the LOMO? Lowest unoccupied molecular orbital. I am leaving this question for the remaining part of this lecture. We will discuss this homo-LOMO concept in the coming slides in detail. From our discussion about the symmetry of p orbitals in 1,3 butadiene, we have deduced 2 very important points. Never forget these points. Always remember that odd number molecular orbitals, wave functions like psi 1, psi 3, psi 5, psi 7 and so on will possess even number of nodes and will always possess M1 symmetry. Why they will always possess the even number of nodes? Because when one is reduced from the psi 1 odd number of wave function of psi 1 like you will get the even number of nodes. So when you will reduce minus 1 from the 5, you will get 1. So the number of nodes will become the even. So when even number of molecular orbital wave functions like Psi2, Psi4, Psi6 are present, they will always possess odd number of nodes and will always have the C2 symmetry. So in summary, for those molecular orbitals for which the value of the wave function is odd, they will have the M1 symmetry. And those molecular orbitals for which the value of the wave function is even, they will have the C2 symmetry. So odd number is attached with the M1 symmetry and the even number is attached with the C2 symmetry. And for the odd number of molecular orbitals, the number of nodes are even, and for even number of molecular orbitals having the wave function in even number will have the odd number of nodes. So these are the two key points that I hope you will never forget. This slide is the repetition of the previous slide. For even number of nodes, molecular orbitals have odd number values such as Psi1, Psi3, Psi5, Psi7, etc. will always possess M1 symmetry, and for odd number of nodes, molecular orbitals have even values like Psi2, Psi4, Psi6, Psi8, and so on will have always C2 symmetry. So this is just the repetition of the previous slide, or you may say that the summary of the previous slide. Before going into the detailed discussion of the symmetry of the p orbitals in some other conjugated system, let us first also discuss the symmetry of the sigma bond. In order to discuss the symmetry of the sigma bond, we are considering a very simple molecule, that is of hydrogen. As we know, according to the molecular orbital theory, the 1s of the two hydrogen atoms overlap with each other, since two atomic orbitals are overlapping, and hence two molecular orbitals will be formed. The one is having the lower energy is the sigma 1s, is called the bonding molecular orbital, and the other, which is having the higher energy, is denoted with sigma star 1s, is called the antibonding molecular orbital. According to the, as we know that s orbital is symmetrical, and mostly to it positive value of the psi is assigned. You may also assign it a negative value. So in the 1s orbital throughout, you will find same sign of the wave function. If sigma 1s, if we take the mirror image of sigma 1s, it will superimposable to the parent image. So it has mirror plane symmetry, since the mirror image of the sigma 1s is superimposable to its parent image. Whereas if we talk about the C2 symmetry, the sigma 1s also have the C2 symmetry. For example, if we take a point from the middle of the sigma 1s and we go suppose 1 angstrom or 0.1 angstrom towards east, and will also go towards 0.1 angstrom towards the west, we will have the same sign of the wave function, since the entire of the sigma 1s have the same value of the wave function. So we may also say that the C2 symmetry is also present in sigma 1s. So sigma, or the bonding molecular orbital, has M1 symmetry as well as the C2 symmetry. Whereas in the case of antibonding molecular orbital, to which I have assigned the name of sigma star 1s, it don't have mirror plane symmetry, because on the one side it has positively assigned lobe, and on the other side it has the negatively assigned lobe. And if we take the mirror image of this antibonding molecular orbital, it will not overlap, it will not superimposable to its parent image. So it does not have mirror plane symmetry. And if we talk about the C2 symmetry, if we move from the center of the sigma 1 star towards the left side, we will meet a blue color lobe having the negatively assigned value of the wave function, and whereas on the other hand, on the opposite direction, if we move towards the right side, we meet positively assigned lobe. So we are not having the same kind of loads on the opposite direction, so the C2 symmetry is also present, is also absent in sigma 1 star. So in summary, sigma or the bonding molecular orbital have the M1 symmetry as well as the C2 symmetry, whereas the sigma star or anti-bonding molecular orbital does not have M1 symmetry, it does not have the C2 symmetry. So both these types of the symmetries are absent in sigma 1 star. Sigma 1 star or anti-bonding molecular orbital. Now very important question is that what will be the symmetry of p orbitals of conjugated ions? For example, cations, anions, and among the radicals. In order to discuss the symmetry of p orbitals in conjugated ions, let us discuss this situation with reference to the allyl and 2,4-pentadienyl system. Chemically speaking, an allyl group is represented with a chemical formula that is shown on this slide. At the bottom of this slide, you may see that the carbon double bond is present between the carbon number 1 and carbon number 2, and a single bond is present between the carbon number 2 and carbon number 3. And additionally, you may see that the carbon number 1 is sp2 hybridized, and similarly the second carbon is also sp2 hybridized. So this is at the bottom of this slide, you may see the chemical representation of an allyl group. The allyl group may either be present either in the form of a neutral form, or it may be present in the form of a carbocation, or it may be present in the form of anion, or it may be present in the form of radical. The three different forms of the allylic group are shown on this slide. In the case of the carbocation, the allyl group possesses three isolated p orbitals, one p orbitals on each carbon. The carbon bearing the positive charge has the p orbital, empty p orbital. Additionally, it has 2 pi electrons that are forming 1 pi bar. In the anionic form, allylic group possesses 3 isolated p orbitals and 1 lone pair of electrons. Similarly, in the radical form, allylic group possesses 3 isolated p orbitals and 1 unpaired electron. All these three forms of the allylic group, that is carbocation, anionic, and radical form, are shown on this slide. One thing that you might have noticed, that all the three allylic forms, that is either cationic, anionic, or radical form of the allyl group, possess one thing common. What is that thing? You might have noticed that all three forms of the allylic group have 3 isolated p orbitals. According to the molecular orbital theory, when 3 atomic orbitals overlap, they give 3 molecular orbitals. When 3 atomic orbitals are overlapping, 3 molecular orbitals should be formed. Half of these should be bonding molecular orbitals and half should be anti-bonding. Out of 3 molecular orbitals, 1.5 should be bonding or 1.5 should be anti-bonding. Is it true? No, that is not true, because we cannot divide the bonding molecular orbitals or any orbital. So my question is, how 3 molecular orbitals can be equally divided? The answer to this question is described in the coming slide. So the question was, how you will divide equally the 3 bonding molecular orbitals as the anti-bonding and the bonding molecular orbitals. The answer is that among the 3 orbitals designated as psi1, psi2 and psi3, one atomic orbital, that is psi2, will not participate in bonding, and hence it will be called as the non-bonding orbital. Now the 2 atomic orbitals, that is psi1 and psi3, are participating or overlapping, and hence they will produce the 2 bonding molecular orbitals. So the 2 molecular orbitals, out of these 2, psi1 will be the bonding molecular orbital and psi3 star will be the anti-bonding molecular orbital. So on this slide I have shown the overlapping of the p orbitals of the allylic carbocation. In the psi1, you may see that the p orbital number 1, I am numbering from left to right. the atomic orbital number 1 and atomic orbital number 2 are overlapping in such a way that the signs of their lobes are in front of each other. That is, the positive signed lobes are on the upper side and the negative signed lobes are on the opposite side, are on the lower side. So there is an effective overlapping because the signs of the overlapping p orbitals is same, whereas the middle one is a non-bonding atomic orbital that is not participating in the overlapping. Here you may ignore the third atomic orbital. So in this way a bonding molecular orbital will be formed that is having n-1 node. N stands for the 1 here in this case situation because the value of the psi is 1. So 1 minus 1 is equal to 0. So this resulting bonding molecular orbital that is generated by the overlapping of the two atomic orbitals, that is psi 1 and psi 3, have no node in it. So you may see that there is a no node in the resulting bonding molecular orbital, whereas here the psi 2, which is shown in the red color, you may see that the two atomic orbitals, that is the p orbital number 1 and p orbital number 3, are overlapping in such a way that their lobes are opposite to each other and hence they cannot overlap to each other, and between these two atomic orbitals non-bonding atomic orbital is present, and hence there will be a one node present between the atomic orbital number 1 and or the p orbital number 1 and p orbital number 2. So it has n-1, 2 minus 1 is equal to 1. So it has one node and its energy is higher than the psi 1. And similarly, if we talk about the psi 3 star, in the psi 3 star, that is anti-bonding molecular orbital, you may see that the two nodes are present. 3 minus 2 is equal to 3 minus 1 is equal to 2. So two nodes are present. First node is present between the atomic orbital number 1 and 2, and the second node is present between the second atomic orbital and the third atomic orbital. The second atomic orbital here in the case of psi 3 star is a non-bonding orbital. You may see that there is a no bond between the p orbital number 1 and a non-bonding orbital, and similarly there is a no bond between the non-bonding orbital and the third p orbital. However, atomic orbital number 1 and 3 can overlap because they have the similar signs of lobes on the same side, and hence they can overlap. However, it has two nodes. Because of it has the highest energy among the psi 1, psi 2 and among the psi 1 and psi 2. So psi 3 has the highest energy and the psi 1 has the lowest energy. What will be the case of symmetry? In the case of psi 1, all the three atomic orbitals you may see are the mirror image of each other. So they possess the M1 symmetry. However, they don't possess the C2 symmetry, whereas in the case of psi 2 you may see that the two atomic orbitals don't have the mirror plane symmetry. They are the center of symmetry. They have the center of symmetry. So first have the M1 symmetry, second has the C2 3, and the third should have M1, as I have told you that you have to assign these symmetries as M1 C2, M1 C2, M1 C2. So first psi 1 has the M1 symmetry, psi 2 has the C2 symmetry, and psi 3 star has the again M1 symmetry. Here again I have shown the symmetries. The psi 1 has the M1 symmetry because all the overlapping atomic orbitals are the mirror image of each other. In the case of psi 2, the two orbitals have the center of symmetry, 2 times center of symmetry, so they have the C2 symmetry. They don't have the M1 symmetry because they are not the mirror image of each other. Again, in the case of the psi 3 star, you may see that the p orbital number 1 and p orbital number 2 are the mirror image of each other, and hence they have the M1 symmetry and they don't possess the C2 symmetry. If we talk about the nodes, the psi 1 don't have any nodes. Psi 2 have a node between the one node between the atomic orbital number 1 and atomic orbital number 2, and the psi 3 star have the two nodes. So the psi 3 star has the highest energy and the psi 1 has the lowest energy. The allyl group may either be present either in the form of a neutral form, or it may be present in the form of a carbocation, or it may be present in the form of anion, or it may be present in the form of radical. The three different forms of the Allylic group are shown on this slide. In the case of the carbocation, the allyl group possesses 3 isolated p orbitals, 1 p orbitals on each carbon. The carbon bearing the positive charge has the p orbital, empty p orbital. Additionally, it has 2 pi electrons that are forming 1 pi bar. In the anionic form, allylic group possesses 3 isolated p orbitals and 1 lone pair of electrons. Similarly, in the radical form, allylic group possesses 3 isolated p orbitals and 1 unpaired electron. All these 3 forms of the allylic group, that is carbocation, anionic and radical forms, are shown on this. Here I have shown the electron distribution in the case of allylic radical. For the case of allylic radical, you may see that the psi1 orbital is the ground state energy level, whereas the psi2 is the HOMO or the highest occupied molecular orbital for the allylic radical, which has an extra electron as compared to the allylic carbocation. So the lowest unoccupied molecular orbital for the allylic radical should be psi3 star. So you may, if you compare the HOMO-LOMO energy orbitals of the carbocation and the allylic radical, then for the allylic carbocation you may see that for it the ground state energy level, that is the psi1 is the HOMO, whereas the psi2 is the LOMO of the allylic carbocation, whereas for the allylic radical, which is having an extra electron or the unpaired electron, its highest occupied molecular orbital is the psi2, whereas for it the lowest unoccupied molecular orbital is the psi3 star. So as the number of the electrons changes, the HOMO-LOMO energy levels of a molecule also changes. Now it's time for the assignment. Fill the electrons in the symmetry energy diagram of an allylic anion and find out its HOMO-LOMO orbitals. You have to inform me what will be its HOMO and what will be its LOMO orbital in the terms of psi1 and psi2 and so on. I am giving you the hint that the allylic anion possess the 4 electrons that should be distributed among the different bonding and anti-bonding molecular orbitals. So best wishes for you. You have to submit these this assignment at my email address m.yasen@ue.edu.pk. Now we are going to discuss the symmetry and the HOMO-LOMO orbitals of 1,3-pentadienyl group. Chemical representation of the 1,3-pentadienyl group is shown on the top of this slide in red color. 1,3-pentadienyl group may be either in the neutral, cationic, anionic or in radical form. In cationic, anionic or in radical form, it possesses 5 p orbitals. In neutral and cationic form, it possesses 4 pi electrons. In anionic form, it possesses an additional electron, and in radical form, it has 1 unpaired electron. Now it's time to discuss a little bit complex pi conjugating system, that is 1,3-pentadienyl cation. In the case of 1,3-pentadienyl cation, each carbon has 1 unhybridized p orbital, and hence 1,3-pentadienyl cation have 5 p orbitals that will participate in overlapping. Similarly, it should have it have 4 pi electrons that are participating in bond formation. According to molecular orbital theory, when 5 atomic orbitals or the p orbitals will overlap, 5 molecular orbitals will be formed. Out of the 5 molecular orbitals, half will be bonding and half will be non-bonding. And since we cannot divide the 5 into a whole digit, so the atomic orbital number 3, that is, if we designate the atomic orbitals as psi1, psi2, psi3, psi4 and psi5, the psi3 will not participate in the overlapping, and hence only 4 atomic orbitals will overlap and will produce the 4 molecular orbitals, out of which 2 will be, that is psi1 and psi2 will be the bonding molecular orbital, and psi4 star and psi5 star will be the anti-bonding molecular orbital, whereas the psi3, which do not participate in overlapping, is called the non-bonding molecular orbital. Now the question is, how many nodes will be present in psi1, psi2, psi3, psi4 and psi5 bonding molecular orbital. According to the N1 formula, psi1 will have 0 node. As shown in the diagram, you may say that all the atomic orbitals are overlapping, whereas in the case of psi2, one node should be present, 2 minus 1 is equal to 1, so one node should be present. So you may see that the atomic orbital number 1 and 2 are overlapping, whereas the atomic orbital number 3 and 4 are also overlapping, whereas the atomic orbital that is shown on the red color on this slide in the case of psi2 is not participating, and hence one node is present between the atomic orbital number 2 and 3. And similarly in the case of the psi3, 2 nodes should be present because 3 minus 2 is equal to 3 minus 1 is equal to 2. So one node is present between the atomic orbital number 1 and 2, and second node is present between the atomic orbital number 4 and 5. And similarly, the atomic orbital number 2 and 4 are overlapping. And similarly, in the case of psi4 star, there should be present 3 nodes because 4 minus 1 is equal to 3. So 3 nodes are present, which are shown in the dotted line. And similarly, in the case of psi5 star, 4 nodes should be present because 5 minus 1 is equal to 4. And these 4 nodes are present in the dotted lines in this diagram. So if we talk about the energy of these molecular orbitals, psi1, which is having the 0 node, will have the lowest energy, and psi5 star, which is having the 4 nodes, will have the maximum energy. Now it's the time for the filling of the electrons among these molecular orbitals. First of all, the lowest energy orbital will be filled, the molecular orbital will be filled, and hence 2 electrons go into the psi1, and the remaining 2 electrons will occupy the psi2. Now, what is the highest occupied molecular orbital? If we talk, there are 2 atomic molecular orbitals that are filled, psi1 and psi2. Among these psi1 and psi2 have the highest energy. So the HOMO for the 1,3-pentadienyl cation will be psi2 of the 1,3-pentadienyl cation. Whereas what will be the lowest occupied molecular orbital? The unoccupied orbitals, molecular orbitals of 1,3-pentadienyl cation are psi3, psi4 star and psi5 star. And the lowest energy among the psi3, psi4 star and psi5 star is of psi3. So the LOMO of the 1,3-pentadienyl cation will be the psi3. So again, it's the time for another assignment. Draw the correlation diagram, energy correlation diagram of the anion and the free radical of 1,3-pentadienyl and locate their HOMO-LOMO orbitals. Now let us discuss the excited states by the example of 1,3-butadiene. The structure of 1,3-butadiene is shown in the red color. How many molecular orbitals it will form? Since 4 atomic orbitals are overlapping, so 4 molecular orbitals will be formed. Psi1 and psi2 will be the bonding molecular orbital, whereas the psi3 and psi4 will be the antibonding molecular orbitals. How you will fill the electrons among these orbitals? When 4 atomic orbitals of 1,3-butadiene overlap, 4 molecular orbitals psi1, psi2, psi3 star, psi4 star will be formed. Psi1 and psi2 will be the bonding molecular orbital, whereas the psi3 star and psi4 star will be the antibonding molecular orbital. In its ground state, the 2 electrons will first occupy the psi1 and the remaining 2 electrons will go into the psi2. In the ground state of 1,3-butadiene, the psi2 will be the highest occupied molecular orbital and the psi3 star will be the lowest unoccupied molecular orbital. When 1,3-butadiene is thermally excited, always remember, when it is thermally excited, the 1 electron from the ground state, that is the psi1, will be excited and will go into the psi3 star. Now what is the situation of the HOMO and LOMO? Now the HOMO-LOMO orbitals are changed. Now the highest occupied molecular orbital for the thermally excited 1,3-butadiene is psi3 star, whereas the lowest unoccupied molecular orbital for the thermally excited 1,3-butadiene is psi4 star. So whenever you excite a conjugated system thermally, the 1 electron from the ground state is excited and it changed the HOMO-LOMO energy orbitals of the parent molecule. Now it's time for the assignment. Fill the electrons in the symmetry energy diagram of an allylic anion and find out its HOMO-LOMO orbitals. You have to inform me what will be its HOMO and what will be its LOMO orbital in the terms of Psi1 and Psi2 and so on. I am giving you the hint that the allylic anion possess the 4 electrons that should be distributed among the different bonding and anti-bonding molecular orbitals. So best wishes for you. You have to submit these this assignment at my email address m.yasen@ue.edu.pk. So at the end of the lecture, here is a summary. Pericyclic reactions are concerted reactions in which electrons move in a circular manner. Always follow the symmetry pattern as M1, C2, M1, C2, M1, C2 and so on. Thermally, electrons are excited from the ground state and the photochemically electrons are excited from the HOMO orbitals. Now it's time for the assignment again. Listen my lecture and search the assignment and quiz that I have uploaded on different slides during the course of this lecture. So you have to listen this lecture and you have to identify the assignments and the quizzes that I have asked on the different slides during the course of this lecture. You have to answer or submit these assignments at my official email address. A list of the books that you may read for further understanding of the pericyclic reactions. I personally like the book written by the Robert T.M. Obert, N.B. Organic Chemistry, Prentice Hall, New Jersey, 1992, 6th edition. So you may consult any of the books listed on this slide.